Differential equations. We're on lesson 5.1, day 6. Moving away from the springs, we're actually going to move to the LR and RC circuits. And we have E, which was the voltage, the impressed voltage. We had L for some inductance and a resistance and a capacitor. That's what the LRC was. Remember from Kirchhoff's second law, the voltage drop from the inductor would be L times di dt, the change in the current, and the voltage drop for a resistor would be R times I, R times the current, and for a capacitor, the voltage drop would be the charge Q at any given time divided by the capacitance C. Now, as you look at this, you're going to notice that we don't have, all the same independent variables. We have an I, we also have a Q. Q is your charge. But the current I is really dq dt. So this second order differential equation right here is what we're going to refer to repeatedly. And we can look at Q really as the charge in the capacitor. A Q would be that charge that is stored. A capacitor will store it, and then it will slowly discharge. So if di dt is given, well, take the derivative. You take the second derivative of Q with respect to time. That's your L second derivative of Q with respect to t. I itself is dq dt. Here's R times dq dt plus 1 over C times Q. You're going to notice now that your independent variable is a Q, and we have a second order differential equation. We could go ahead and solve this second order differential equation with a characteristic equation. And of course, we would use a quadratic equation to do so. You can see we've got the quadratic formula. And, what you could more or less see is that your A, well, first off, is we'd look at the characteristic equation. That would be Lm squared plus Rm plus 1 over C would equal 0. And, at this point, we could say A is equal to L. B would equal R, and your C would be the 1 over the capacitance 1 over C. But the reason why we jotted down this quadratic formula is because so much of what's about to happen in regards to what type of a system we have will be dependent on what's happening inside that square root, that is the discriminant. So if your discriminant is positive, if b squared minus 4ac, that is if r squared minus 4 times L times 1 over C, if that's greater than 0, the system is overdamped. We would not see the oscillatory motion. We'd see that, we wouldn't be getting our electrical, measuring that charge there. We wouldn't see that being in terms of a sine wave or a cosine wave. If that discriminant were to equal 0, we'd be critically damped, and the graphs would look very close. What happens very often, what you definitely will see happen, is r squared minus 4L over C. If that is negative, if it's less than 0, you're going to be underdamped. And remember what underdamped would look like on the far bottom right portion of the screen. We'd see a graph that looks like this. So, of course, you've seen, I hope that as you study electricity, sine and cosine have their applications there as well as you were to graph out an alternating current. But as you can see here, this would be considered underdamped. If, of course, E of t is equal to 0, electric vibrations are said to be free if that right-hand side was to equal 0. So what we've got right here is, okay, so let's look at this situation. Find the charge Q of t on the capacitor in an LRC circuit when L is equal to 0.25 henries, R is equal to 10 ohms, and the capacitance would be 0.01 farads. And of course, E, the voltage, would be 0. So what we could do from Kirchhoff's second law is immediately jot down what we just saw in green. And instead of writing the second derivative in the first style, we'll just write it with the primes. What you can see very quickly is L is equal to 0.25, and we could have our resistance is 10, and then of course this would be 1 divided by 1 over 1,000. And you know that E is equal to 0. That's on the right hand side. Normally E is right over here. But just as important, we don't want to lose sight of our initial conditions. Q of 0 should equal Q naught. This thing right here should be Q sub 0. And when we take a look at IO, when they're giving you IO, of course they're saying the current. That's really dQ dt is equal to 0 when t is equal to 0, right? So, of course, we can go ahead and solve this. And, as we do, we could say this is 0.25 q double prime plus 10 q prime. You divide by 1 over 1,000, you're really multiplying by 1,000. And, it doesn't take long. If you multiply everything, 0.25 is 1/4. If you multiply everything by a 4, you quickly are going to see that you have this very nice and simple second order differential equation. Of course, we could get a characteristic equation right over here. So m squared plus 40m plus 4,000 is equal to 0. Well, either solving with the quadratic formula or solving with our 89s with C-solve, we could say m is equal to negative 20 plus or minus 60i. And, that would be an underdamped system. And what we're going to be able to do then is very quickly realize that Q, that's what we're solving for here, would be e to the negative 20t, and then we'd have c1 cosine of 60t plus c2 sine of 60t. So we have two initial conditions that we're going to revisit. We knew that q of 0 was equal to q naught, and we knew that q prime of 0, as we saw up here, would equal 0 as well. And of course, I wrote it originally as dq dt. Well, let's go ahead and see if we could find what these constants could look like. Using our first, initial condition, we'd say at t equals 0, q would equal q naught. So we'll have q naught on this left-hand side. Now, of course, anytime we take e to a 0 power, that's going to be a 1. And of course, cosine of 0 is going to be a 1. So we'd be left with c1 times 1. But the sine of 0 right over here would be a 0. So it doesn't take us too long to see that that first constant is actually q sub 0. So we're well on our way and by the way, you could and should, in fact, right now feel free to go ahead and plug in that constant c1 and just write it as q sub 0. We're almost done. We just have to find what the second constant actually would look like. So what you need to do is now use your second initial condition. Q prime of 0 would equal 0. So we're going to take our derivative, q prime, and of course that means we're going to need the product rule. So we could have our e to the negative 20t, that's our original u, and then we'll take our derivative of v. And as we do that, the derivative of cosine is negative sine, but we're going to need the chain rule to be applied. So out comes a negative 6c. When we take our derivative over here, of course, we're going to say the derivative of sine is cosine. But again, the chain rule is going to apply. And without too much work, we're going to have this. Please understand that's just your uv prime. Now we'd like to say u prime, which taking the derivative of e to the negative 20t, well, this time our chain rule is going to bring a negative 20. The derivative of negative 20t with respect to t is just negative 20. And then we're going to have to keep our v the same. So, wow, at this point, I hope you can see we're so close to being done, but that initial condition is saying that when t equals 0, q prime equals 0. So what's going to happen? Well, we can see that the left side is going to become a 0. This e to a 0 power, of course, just becomes a 1. Sine of 0, this thing right here, is going to completely wipe out to just be a 0. But the cosine of 0 works out to be a 1, so we'd get 60 c sub 2. Then, when we plug in our 0 right here, e to the 0 is in fact a 1, but don't forget, we do have that negative 20 out in front. The cosine of 0 is, in fact, a 1, so we'd have a 1 times q naught. And then, of course, the sine of 0 is just a 0. So things are cleaning up in a hurry. I think you could see that 1 times all of that parentheses is just 60c sub 2. And then over here, we'd have a minus 20 q sub 0. So if I'd add a 20q sub 0 and then quickly divide by 60, you'd get c sub 2 would equal 1/3 q sub 0. Now, what that really means is go back up to the top where you see here, and you can say, well, I used my first initial condition to find C1. I now know what C2 is. So just finishing that up, we could say Q is equal to E to the negative 20t, Q sub 0 cosine of 60t. My C2 is actually Q naught over 3, 1/3 Q naught, times the sine of 60t. And that is the end of this chapter.